This is the lecture video for MAT1100, and this is lesson 1.6. And in this section, we're going to be looking at the fundamentals of probability. We're going to look at some of the terminology that will be used with respect to probability, and also look at various types of common examples that you would see in a section like this. Okay, first to fill in some of the terminology that you're going to be seeing. Any occurrence where the outcome is uncertain, such as tossing a coin. You don't know whether it's going to come out heads or tails. You know it's one of those. So it's an occurrence where the outcome is uncertain, and that's what we refer to as probability. Okay, the set of all possible outcomes that could possibly happen. Well, in the case of tossing a coin, the only possible outcomes that you could have is either a head or a tail. So when you list all the possible outcomes, this S that you see right here stands for sample space. An event is the desired event we're looking at. Like perhaps you want to know, what is the probability of tossing a head when you toss a coin? So that would be the desired event. So any subset from the sample space, this is such as tossing a head, is just part of this sample space, and that's what we call an event. You see that symbolized by E. S stands for all the possible outcomes, also known as the sample space, and the event that we are looking for just refers to the desired event that we are looking to, that you're looking to have for it to happen in that particular problem. And yeah, I'll point it out to you as we do the problems. Okay, so blank only applies to situations in which the sample space only contains equally likely outcomes, all of which are known. So this is what we refer to as equally likely events. Okay, theoretical probability. If an event symbolized as N sub E, equally likely outcomes, and its sample space has equally likely outcomes, then the theoretical probability of any particular event is denoted as the probability of a particular event. And you'll understand this way better when I start to do the problems. I'm going to point out to you the kind of symbolism that we use to indicate what kind of probability we're doing. So let's look at some of these problems that are on the next page. Okay, I'll come back to this and talk about this. But basically what you are seeing on this line here is that probability can be anything from, it can turn out to be anything from 0 all the way to 1, and never any bigger. So when it is impossible, let's say that I said, what is the probability of, for instance, let's say you had one of these dies, a 6-sided die. Die is just a singular, meaning you have one die. So let's say you roll it and it's got 6 sides. One side has a single dot, one side has 2 dots, one side has 3 dots and 4 dots, 5 dots, 6 dots. So let's say that I posed this question to you knowing that what you're throwing is a 6-sided die. So you can't have, it cannot land in any way other than for 1 dot to show, 2 dots to show, 3 dots to show, 4 dots, or 5 or 6. So what if I say, what is the probability of this die landing such that a 7 shows? What is the probability of rolling a 7, a side with 7 dots? Well, the probability would be 0. That is impossible for that to happen when you're rolling a 6-sided die, because none of the sides have a 7 on it. So a probability can be as low as 0, which means the event is impossible. That's what that means. But it can also be as high as 1. Like for instance, how about if we talk about concerning a 6-sided die? Same thing. We're going to roll that. And what if I was to ask you, what is the probability of rolling a number between 1 and 6? When you point these symbols in the same way, that's read in between. So maybe you should write that so you can understand it later. What is the probability of rolling a number between, this is if you write it out in words, rolling a number between 1 and 6. And here's how you set up your fractions for probability, because probability, they are written as fractions, and this is how the fraction goes. Total number of outcomes goes on the bottom. There are 6 different ways that a 6-sided die can land. Total number of outcomes on the bottom. And then the top is number of desired events or desired outcomes. You can speak of it in either way. Okay, well, if you're looking for a number between if you're looking for a number between 1 and 6, there are 6 desirable outcomes. If you roll this die and it lands with 1 dot up, that's desirable. If you roll it and 2 dots show, that's desirable. In fact, every single number, let's see, and it could be equal. Let's say I'm looking for anything that's between 1 and 6, or it can be equal to those endpoints. Then every single number is desirable, the 1, the 2, the 3. So you have 6 desired events out of a total of 6 possible events. And so in this case, when we're talking about what is the probability of rolling a number on a 6-sided die such that this number is in between 1 and 6 but can include the 1 and the 6. That means that all 6 events out of a total of 6 are desirable, and that's when your probability can come out as high as 1. So it can be as low as 0, never any higher than 1, but and also anything in between 0 and 1. Okay, so regarding what we were talking about just now, we can fill in these very easily now that we've discussed the die with 6 different pictures on it. One side has 1 dot, 2 dots, 3 dots, etc. So the sample space, this is the sample space. You could have a face that looks like this. You could have a face that looks like this. You could have a face that has 3 dots. You could have a face that has 4 dots. You could have a face that has 5 dots. Or you could have a face that has 6 dots. Okay, that's your sample space. Those are the 6 possible ways that the die can land. What is the probability? What is the event of rolling a number from 3 to 6? Let me move to the next page. Hold on 1 second. Okay, all the numbers that satisfy this, anything from 3 to 6, the number 3, the number 4, the number 5, and the number 6. And you don't actually have to draw pictures for them. You could have just put the face with a 1 on it, the face with a 2 on it, the face with a 3 on it, the face with a 4 on it, face with a 5 on it. You can just use numbers to represent that it landed on a face with that many dots on it, 1 dot or 2 dots or 3 dots or 4 dots. Okay, this represents the face with 3 dots, 4 dots, 5 dots, 6 dots. So just giving you, you haven't been asked a probability there, but I already kind of pushed you ahead so that we could talk about two different kinds of probability. Probability of rolling a 7, impossible. So you have a 0 chance of that happening. Probability of rolling anything between 1 and 6 where it can actually be these endpoints, the 1 or the 6. Well, all 6 faces out of a total of 6 were good. So we pushed ahead and did probabilities there. And then finally you get to this problem and you're doing another probability. What is the probability of getting a number less than 5? And they can write it out in words like that, or they can use this shorthand abbreviation. What is the probability of rolling a number less than 5? Okay, so you got to think about what satisfies this. The face with a 1 is less than 5. The face with a 2 is less than 5. The face with a 3 is less than 5. And the face with a 4 is less than 5. Now, since they said less than 5, that means it can't be 5. So there are 6 possible faces. Remember, always put the total number of possible outcomes on the bottom. And then how many events are desired? That's in a desired event. This is a desired event. So there are 4 different faces that have a number that is acceptable because these numbers are all less than 5. So 4 out of the 6, and these are called the desired outcomes. There are 4 desired outcomes that satisfy being a number less than 5. So that's your probability. Probabilities are fractions. Now, yes, you can reduce them. 2 goes into the top here twice. 2 divides into the bottom 3 times. So this would be your answer, all reduced. Okay, then being asked questions about a deck of cards. That's a pretty common type of problem when you're talking about probability. So I guess it would be good to remind you what are the different suits in a deck of cards and how many do you have of each suit. Okay, first of all, there are 4 suits. There are hearts, and you have 13 of those. Within this suit, you have a jack. Within every suit, you have a jack, a king, a queen, and an ace. And then there's all the cards that just have numbers on them. But the ones that have pictures on them are the jack, the king, the queen, and the ace. All of these belonging to the family of hearts, also known as a suit. You also have the suit or family of diamonds, and there are 13 of each family, each suit. And there's also a jack, a queen, a king, a queen, and an ace. So this would be the jack of hearts, the king of hearts, the queen of hearts, and the ace of hearts. Same thing here. Only this would be diamonds. So the jack of diamonds, the king of diamonds, the queen of diamonds, the ace of diamonds. Anyways, just in case you don't play much cards and you don't know this, there's also a suit called clubs. Can't draw this very good, so please forgive my drawings. So I'll let that be the picture of clubs. There are 13 likewise. There's a jack, a king, a queen, and an ace. I'm not going to draw the little pictures here. Okay, then there's also the spade. Spade kind of looks like this maybe. Kind of my estimate at what it looks like. And there's 13 of these, again, with a jack, a king, a queen, and an ace. These would all be the jack, king, queen, and ace belonging to clubs, and this would be jack, queen, king, and ace belonging to spades. So when they ask you a question and you know what to expect in a deck of 52 deck of cards, 13 times 4 is 52 because there's 4 suits. Find the probability of being dealt a king. Well, there's a king here, a king here, a king here, and a king here. So what is the probability that if you dumped an entire deck of cards in a hat and had somebody put their hand in and pull a card out, what is the probability that they would pull a king out? Well, total number of cards in the hat, total number of outcomes is 52. And only 4 of them are desired outcomes. So this would be your probability of drawing a king out of a hat that contains all 52 cards. Again, you should reduce these to get full credit on your answers because we're expecting that you know how to reduce fractions. You can divide the top by 4 as well as the bottom by 4, and on your calculator you should have a key that reduces. So 4 divides into 4 one time. 52 divided by 4 is 13. So this is the most reduced version of the answer. Okay, so more probability. Okay, then I would like to talk to you about theoretical versus empirical. So with theoretical probability, like for instance, let's say, you know, that I ask you and you don't try to collect any information, you don't make a table of outcomes. If I just ask you, what is the probability of tossing a head, tossing a coin and making it land heads up? What's the probability that it will land heads up? Well, there's 2 possible faces on a coin. And only one of them is the desired outcome of the head. 1 out of 2 outcomes is the head, has the picture of the head on it. So this is what we refer to as theoretical probability, as opposed to when you're doing experimental probability, also known as empirical probability. You're actually going out into the field, collecting data, organizing it in a table, then doing the probability. So theoretical probability, no data collected in a table. You will not be collecting data in a table. Let's just say no data collected in table form. Okay, so you could keep your hands in your pocket, never collect any data, and you'd be able to say that the probability of a coin landing heads up is 1 out of 2. Now they could ask you a question like this. They could say, well, what if you toss a coin, but you don't actually toss it? They say, what if you were to toss a coin 80 times? You already know that it has a 1 out of 2 chance of landing on a head or a tail for that matter. If you toss a coin 80 times, how many times would you expect to get a head, for it to show the picture of a head? Okay, so what you have to think about is that the probability of tossing a coin just once and the probability of you getting a head is 1 out of 2. But if you're going to toss it 80 times, then it would be that theoretical probability. And when they're just saying expect, that means you're not basing this answer on data that you've collected. You could actually answer the question just by going 1/2 times 80 and never actually tossing a coin. So when we're not collecting a bunch of real live results, we call this theoretical probability. So you would just go 1/2 times 80. You could put this in your calculator, and you could just go, 1/2 is the same thing as 0.5 times 80, and you would get 40. Half of 80 is 40. So you would expect to see a head 40 times. And this is another example of theoretical probability. Again, you are not collecting data in a table. Okay, on the other hand, let me give you an example of empirical probability, because they're going to really come at you in ALEKS, making sure that you know the difference between theoretical probability and empirical probability. So here is an example of empirical probability. I'm going to put it down below. We'll come back and fill out these blanks. Okay, with empirical probability, they'll tell you you rolled the die, a single die, 300 times. And each time you rolled it, you recorded what face showed on the die. And the results have been gathered here for you in the following table. Okay, so here's the table. Okay, now let's see the different ways that the die could land. It could land with one dot. So these are the number of dots. It could land with 2 dots up, 3 dots showing, 4 dots showing, 5 dots showing, or 6 dots showing. Okay, so in this table, we have these different categories. Now this die was rolled 300 times and the results were collected in this table. As far as throwing that die, how many times did a 1 actually occur during this 300 times that the die was rolled? It turns out that a 1 showed 46 times. So each time the person's rolling it and keeping track of how many 1s, how many 2s, how many 3s, and then they summarize the results in a table. The 2 landed. It landed on the face with 2 dots 39 times. It landed with 3 on the face with 3 dots 45 times. 4 dots showed 62 times. 5 dots ended up showing 60 times. And 6 dots ended up showing 48 times, for a total of 300 rolls. Altogether, this was 300. This is what we call either experimental or empirical. Those mean the same thing. It's just another way of saying empirical is the same thing as saying you conducted an experiment. You collected the results. So when you do a probability like this, it's still desired outcomes. Let's say we're trying to answer what was the probability based on these results of rolling a 6. Well, total number of outcomes was 300. You actually rolled it 300 times. And out of those 300 times, this desired outcome, rolling a 6, occurred 48 times. And you can even give that as a decimal. You could reduce that fraction. And it would be 4/25. You can even give it in decimal form. You could either enter this divided by this, or you could enter this divided by this, because this and this are equal. So you can give your probabilities in decimal form even. 4 divided by 25 is 0.16. So just different ways to give it. But anyway, when you have calculated a probability based on results that were collected from a true experiment that was conducted, where you actually kept rolling it and recording what showed each time, that's referred to as experimental or empirical probability. Let's go ahead and fill in these blanks here. So that you have the terminology that you're going to see being used in ALEKS and in your book. A coin that is equally likely to land heads or tails is called a fair coin. Empirical probability can actually be used to determine if a coin is fair. They could actually keep tossing it, collect the results, and if it comes out too slanted where you're getting too many tails or too many heads, it's not a fair coin. Because this is actually what happens when you do collect data in an experiment. Okay, the following happens. And this will be a question in ALEX also. Theoretical probability and this is theoretical, oops, sorry about that, theoretical versus empirical or experimental. I'll put experimental versus experimental. Just know that they can use the word empirical. Okay, so we're comparing theoretical to experimental probability. And what has been found, which is why you can use this as a technique to determine whether a coin is actually fair or not. Because when you conduct an experiment like that, you already know that the probability of rolling a 6, if you didn't toss this thing 300 times, just if you had the die in your pocket and somebody said, what's the probability of rolling a 6? 1 out of 6. There's only one face that has a 6 on it. That's what we would call theoretical. Keep your hands in your pocket, don't do anything, don't collect any results, and you would still know that the probability of rolling a 6 is 1 out of 6. Now, how close is it to that? Let's see, because we're going to compare when do those two answers, theoretical probability and experimental probability, when do they get close? What makes them get closer and closer? So just a theoretical probability instead of 48 out of 300 would have been 1 divided by 6. That's pretty close to what you got here. So, what you just proved is that this is a fair die. Not slanted in a way that's going to make it land on a certain face each time. So what we say here, and like I said, there's going to be a question in ALEX, is as an experiment is repeated more and more times. So the more times you repeat a certain experiment, and in this case it was rolling a die, the closer the empirical probability, well, we got to fill this in. The experimental or empirical probability, you can use either of these words. The experimental probability of events, and this is as an experiment is repeated more and more times. The empirical or experimental probability of events gets closer to the theoretical probability. It will actually occur that as you do more and more repeated attempts to see whether or not you're going to get a 6 or not, the bigger this number gets, the closer your empirical probability or experimental, you could call it either one, gets to the actual theoretical probability, which is the kind of probability that you could do without collecting any kind of numbers. Just 1 out of 6 is a probability of getting a 6. And they get closer and closer as your experiment is repeated more and more times. And we actually use that to figure out whether it is a fair object that we are using, a coin or a die. Okay, here's another problem that they could potentially use in order to ask you some probability type questions. This is a spinner. You're going to flick that spinner and it can land on any one of these. So you have some gray pieces right here, you have some white pieces, and you have some blacks. Okay, so now look what happens. In this particular problem, they're doing, I'm going to use the word empirical now because I want you to get exposure to using both of them. You could either use empirical or experimental. But notice that they're collecting the data in a table. So understand that that is the essence of empirical probability. Whereas theoretical, you don't collect any data. You're not doing repeated occurrences of anything. So here's all the data here in the table, and they're saying that what happened is that it was spun. Somebody spun the dial 20 times, and they collected the 20 results here. Doesn't have to be 300 times, but they're actually doing an experiment and collecting the results here. So now the question is, in part A, for Melissa's results, compute the experimental probability of landing on a black. Okay, well that means that you are doing your probability from the results in the table. That's what makes it an experimental probability. Okay, because you're answering from the table, because you could also answer just from this diagram. And in that case, you're not really flicking it. You're not recording any results. You're just looking at the way the diagram looks. But if you're going from the values that are in the table, that's experimental probability, and that's exactly what they're asking you to do in part A. From Melissa's results, compute the experimental probability of landing on a black. Well, it was spun 20 times, so that's the total number of outcomes. And then according to the information collected here, we're concerning black, 3 times it landed on black. So that right there is your experimental probability based on this collected data in the table. Part B, assuming the spinner is fair, now compute the, we did experimental probability right from the table. Compute theoretical probability of landing on a black. That means you are just looking at the diagram here of the circle. Just looking at the diagram. If you wanted to do the probability based on that, then it's probability of black. Well, how many blacks here are there? There are 10 different sections here, and there are 2 black sections. So it's 2 out of 10. So this is the probability of black when you use the experimental information. This is the probability of black when you're doing it right from this diagram and not looking at these numbers. This reduces to 1/5. Okay, 2 different answers, experimental versus theoretical. Assuming that the spinner is fair, choose the statement below that is true. As the number of spins increases, and this is assuming you're doing an experiment, as the number of spins increases, we expect the experimental and the theoretical probabilities to become closer. That is always what happens as you repeat your experiment more and more times. Same question asked on the previous page. If you're going to conduct that experiment more and more and more, this probability, this experimental probability, will get closer and closer to the theoretical probability, where I just did the probability right off the diagram. Okay, so that's parts A, B, and C. This would have been the wrong choice. The experimental and theoreticals must always be equal. No, they aren't. As you increase how many times you actually collect data in your experiment, number of spins in this case increases, then experimental and theoretical get closer and closer. And that's how we determine fairness. So that concludes the lecture for lesson 1.6.